Now, chapter number 4, Poisson's equation, Laplace equation, and boundary condition, Uniqueness Theorem, and classical image problems. Now, in this chapter, we are going to study these topics about Poisson's equation and Laplace equation. First topic. Now, by Gauss law, we know that divergence of electric field del dot E is equal to rho by epsilon naught. The electrical potential, as we have defined before, is equal to minus of gradient of scalar function V. E equal to minus of gradient of scalar function V. Now, if we substitute in place of E minus of gradient of V, we will get del dot minus del grad of V is equal to rho by epsilon naught. That is, del square V is equal to minus rho by epsilon naught. This equation is well known as a Poisson's equation. Now, in the region of this space, there is no charge. If there is no charge, this rho terms get equal to 0. Poisson's equations will come down to the Laplace equation. That is, del square V is equal to 0. Now, Laplace equation in one dimension and two dimension. To solve the Laplace equation in one dimension, consider that potential depend upon only one coordinates of the Cartesian coordinate system, for example x. The Laplace equation will equal to d square by dx square V is equal to 0. When we integrate it, we will get dv by dx is equal to a constant integration constant a. Again, we will integrate it, we will get v is equal to ax plus b, where b is another integration constant. Now, Laplace equation solution in dimension 2. In two dimension, the Laplace equation becomes the in two dimension, it depends upon two variables x and y. Therefore, the function d by square phi divided by d by x square plus d by square phi divided by d by y square is equal to 0. Since the derivative is partial, we must have equal to a constant. Now, the solution is thus the solution of the equation is become this one. Now, if we put this solution and draw the graph of potential as a function of x and y, then it will कुछ इस हद तक ऐसा दिखेगा. That is not minimum, not maximum. It's like a horse saddle. Now, there is a saddle point at point x equal to 0 and y equal to 0, where they get come. जिस तरीके से सैडल के बीच में आता है और फिर ऊपर जाता है, तो वो बीच का जो हिस्सा होता है वो यहाँ पर आपको दिखेगा at x equal to 0, y equal to 0. That is known as a saddle point, where the function rise in one direction and decrease in another direction, like the saddle on the horse, where the seat slope downwards along the back but rise along its length both forward and backward. Mathematically, in two dimension, if the function is partial derivative, then function has a saddle point. At this point, what we call as a point 0, 0 in this case. The expression is at x equal to 0, y equal to 0, minus of a square divided by 4. Boundary condition. Now, in a partial differential equation like Laplace, Poisson's, the solution in the form of summation am, fm, where am is a constant, fm is a function of multiple function, m is the number of integer that has to be counted down. Then the solution has a many constant. So constants evaluate the specific value, specifying the value of function fm at the border of the region. There come what to consider and what to not. So we have to define a boundary under which we have to operate the function. These value at the border is known as a boundary conditions. we have to put the constraint actually, how we will define that constraint, how much body you wanted to operate on, by the some function or by the some field, and see the effect of that field. That is what we call as a boundary condition. Now, uniqueness theorem. According to the boundary condition, we have a uniqueness theorem. The proof that the set of boundary conditions is sufficient to give the unique solution to a practically partial differential equation is presented by the uniqueness theorem. There are two types of uniqueness theorem. First uniqueness theorem, second uniqueness theorem. The solution to the Laplace equation within a volume is uniquely specified if the potential is specified along the boundary of the surface of the volume V. If we have potential at the boundary of the surface of the V, surface named as V, then we have a potential of a specified name, specific value. Here we are finding the potential of the function. Whereas in second uniqueness theorem, the electrostatic field has to be taken in account. The electrostatic field in a volume V containing the specified charge density rho surrounded by one or more conductor is uniquely determined if the total charge on each of the conductor is known. Now, classical image problems. Depends upon the boundary condition and uniqueness theorem. There is a classical image problem. These are the problem actually, and we have applied these two and find a solution. Now, first problem, charge near the infinite conducting plane. Let's suppose I have an infinite conducting plane. I had a charge Q over here, placed at the distance t from the plane, and I wanted to find the electric field, electric potential at this point P. Okay. Now, problem says that consider a charge Q placed at the distance d above the infinite conducting plane, that is earthed. I have make it ground, earthed. Find the potential, electrostatic field, surface charge density, total charge induced, force, potential energy, etc. at the point P. Now, when we look it into two dimension like this, side view, our charge Q is over here, our infinite plane is this xy plane, and this charge is in a z direction, is placed here. Okay, what you will find? You will find the field is perpendicular to the surface and your charge is Q over here at the distance t from the surface of the infinitely conducting plane. Okay, on this we have Vx, y, z की वजह 0 since it's a origin point for z equal to 0, and x, y, z when both तीनों 0 conducting plane rho sigma. Now, for the mirror reflection, if I take the problems, that means if I put it Q plus over here, Q minus over here, Q plus over here, Q minus over here. Then what happens? The charge will start from positive charge Q and ends on negative charge Q. This charge minus Q is imaginary. It's not exist. It's just my imagination that there is a charge again with the minus q at the distance d. Now, mirror effect of the problem is that there is a positive charge q, which is actual charge, and exactly opposite to the positive charge there is a negative charge. Line of forces started from the positive charge and ended on the negative charge. Now this negative charge is imaginary. It is at the same distance d as the q is at distance d from the xy plane. This is the xy plane right now. Now we will make it more simpler diagram, and here it is a simple diagram. The origin charge q, positive charge, and imaginary charge minus qh minus d. As you can see through the diagram, point P is in air, you can say YZ plane. Okay, at this point we have to find the field and the potential and other things. Okay, now mathematically if we try to find the constraint, then the voltage potential is 0, z equal to 0 at z equal to x, y, z equal to 0. Now, if we draw the radius, sorry, if we draw the position vectors from the origin O, and there is a r vector, position vector for the point P, and there are two more vectors, r1 and r2 from the charge, positive charge q and minus q. Now, this r1 vector is actually the summation of r1 prime vector from the origin O to the point Q, positive Q, and minus of this r vector, position vector of the point P. With this with the help of this triangle, the r1 vector is equal to r vector minus r1 prime vector. The similar manner, the r2 vector is also r2 equal to r vector minus r prime vector. If we try to find the potential at point P, which is due to the positive and negative charge, the potential V is equal to potential due to the positive charge plus potential due to the negative charge. By the formula of potential, we have V positive for positive charge Q divided by 4 pi epsilon naught R1, this R1, and for my negative charge q divided by 4 pi epsilon naught r2. Now if we substitute the value of r1 and r2, since q by 4 pi epsilon naught is common term, we will take it out. 1 upon r1 is nothing but in Cartesian coordinate system x square plus y square plus z minus d z is the position of the point P, okay, minus of d, how much d has been passed, because we have to take it from this point, and this is for z plus d, or total term z, position vector of point P, and plus this term, this length below the origin d. Now, in order to prove that the boundary conditions satisfy, let's suppose and consider at point z equal to 0. We will substitute the value of z as a 0 in the equation. And what we find after substituting the value of z equal to 0, these two terms in the brackets are same. and that result, that potential at z equal to 0 is equal to 0. That means we satisfy the boundary condition that at z is equal to 0. That means in xy plane where we have kept the conducting plate, infinite conducting plate, potential at that conducting plate is equal to 0. So similarly, if we look for z equal to infinity, the same terms will becomes um, infinity in denominator, and when it comes in numerator it will be 0. 0 minus 0 is equal to, you will result into the 0. Now once you find the potential equation for the problem, it is very easy to find the electrostatic field. As you know that electrostatic field is the gradient of potential, and in this problem xy plane there is no change in potential. Potential remains constant as v equal to 0. So there is only change in z coordinates, and therefore we will find the electrostatic gradient in z direction. This is the potential equation which we have drawn, and we will take the derivative with respect to z. When we take the derivative with respect to z, we will try to find the potential electric field, because electric field is minus grad of potential. Now यहाँ पर हम we will take change of potential with respect to z coordinate only. Okay, and when we substitute the value and take the derivative of this particular bracket, we come out of this and resulted into this equation. Okay, now in order to prove that the boundary conditions satisfy, again let's consider at z equal to 0 what is the potential, sorry, what is the electric field. So we will find that electric field is equal to Q 1 upon 2 pi epsilon naught minus d divided by x square y square d square raised to 3 by 2. Now negative signs indicate that the electrostatic field which is perpendicular to the plane is directed into the surface of the plane, into the xy plane, into the conducting plane. Now surface charge density, next term, once we know that electric field, then it is very easy to find the surface charge density. As per the Gauss law, we know that the conducting plane having potential as a sigma divided by 2 epsilon for single plate. Therefore, we will find potential as a q by 4 pi epsilon naught minus of 2d divided by x square y square plus d square raised to 3 by 2 dot sigma, which result into this. Now, total charge induced in a conducting plane. Second, we have to find the what is total charge induced. Now, charge we know is nothing but equal to charge density into area. Now, charge density sigma, since it is in a plane, the conducting plate is in the xy plane, and area is 2 pi RL. RL rather than taking RD, as RD is R is nothing but x square plus y square, let's suppose, and RD is the change with respect to plane. We find the we have an equation of Q sigma. We will substitute that sigma equation 2 pi RD. When we do the mathematical calculation, 2 pi get cancelled. Okay, and minus d will become out. Minus QD is outside, and we will calculate this RD divided by R square d square raised to 3 by 2 integration, and we will find that it is nothing but 1 upon under root of R square d square, and range goes from 0 to infinity. When we substitute this value, we will find that capital Q is nothing but the charge at the distance Q, positive Q, which is actual our charge. This shows that the point charge induces an equal and opposite charge on the plane, which is equal to the imaginary charge. Now, when we have to find force, we know Coulomb's law. Coulomb's law said that force equal to 1 upon 4 pi epsilon naught Q test charge into capital Q divided by R square. For this case, we will take R square is nothing but the distance between these two main charges, imaginary charges, and original charge and imaginary charge. Therefore, QQ divided by 2D square. Now, capital Q, as we already know, that is nothing but the small q. So we can make Q square, and we will find the force equation like this. Now, potential energy. Potential energy is the work done bringing the charge from infinity to that point D. Okay, so the force that acts to bring that charge up to the length D is then nothing but the potential energy. If we integrate the force equation, where 1 upon 4 pi 16 pi epsilon naught is a constant quantity taken outside, and Q square is also a constant quantity taken outside, 1 upon Z square, because the movement will be in a Z direction. In XY plane, we have a complete conducting, infinite conducting plane, so we will not take the integration in xy plane. And when we take 1 upon z square d integration, what will happen? 1 upon z square d is nothing but minus of 1 upon z in the range from infinity to the point D. And when we calculate, we will get the potential energy is equal to minus q square divided by 16 epsilon naught d. With this, the conducting plane problem finished. The next problem is charge near the grounded conducting sphere. Now, when we take this problem says that point charge Q is situated at a distance A from the origin or from the center of the grounded conducting sphere of a radius capital R, which is less than A. Now find the potential outside the sphere. Now, according to the image problem, consider again an imaginary charge minus Q situated or placed in a y plane only. In which plane we have kept the positive charge? In y plane only, inside the sphere at the distance B. This distance from the origin is B, and B is less than R. Now collinear with the positive charge, such as this one. And the potential at R equal to capital R is nothing but earth, that is grounded. We will draw the vector formula. Now, here you will see that one vector is from origin, and let's suppose we wanted to find the potential at the point A. Now, from this origin O to the point A, there is one vector. One vector from minus imaginary charge minus Q to that point, and one vector from P to that point. Now, potential at any point outside the A grounding conducting sphere due to the actual and imaginary charge is given by due to the effect of both charges. Now, potential equal to 1 upon 4 pi epsilon naught charge, positive charge Q to AP, and plus positive charge, sorry, imaginary charge q prime divided by qd, AD. This point is D. As you can see, this point is D. Okay, DAD, this green line. Now AP is nothing but R square A square minus of 2RA cos of theta. Similar way AD is equal to R square B square 2RB cos of theta. Now at R equal to capital R, what we have said? We have said the potential is grounded, is equal to 0. We have kept that at R equal to capital R, V is equal to 0. Therefore, the equation, let it be to be 0, and what we find, Q by AP is equal to minus Q prime by AD. Now if we cross multiply it, we will get this equation, and when we substitute these values in the equation, we will further classify. Let capital R to be taken out from this term, therefore Q R A, and let a small a term to be out from this term, and what we find that these two equations are comparing these two equations, what we conclude that QRA is nothing but equal to minus of Q prime A. Simply implies that Q prime is nothing but minus of QRA divided by A. Second, what we conclude that B by R is nothing but R by A. That means B is equal to R square by A. Hence, if we substitute in prime equation that Q prime divided by AD, now Q prime divided by AD is equal to QR capital A. Now we have to put prime, Q prime values, that is minus of QRA divided by A, and in the place of B we will keep the R square divided by A. What we will get? We will get this particular equation, and when we solve it completely, the Q prime divided by AD is nothing but minus of Q divided by capital R square, A square divided by capital R square minus of 2RA cos of theta. Now when we substitute that value in the potential equation over here, so we will get this result. Okay. Now this is the potential at point P due to the charge point, positive charge situated at the distance A away from the center of a grounded conducting sphere of radius capital R less than A.